In the previous video, I went over how to set up the work coordinate system for this test part that we machined in class, or that I demonstrated for you being machined in class. And so we have the origin here and the x-axis along this side of the piece, the y-axis going back here, and then the z-axis going up there. Setting up the work coordinate system is the first step before moving on to the actual creation of the tool paths for machining. So now that we have the part held in the vise, as shown here, as you saw in my demonstration, the machine comes down and cuts these different features on the test part here. The features that we have are just this little rectangle with filleted corners, this circle here, and then these holes here. The larger features, the rectangle and the larger hole, or the circular hole, will be actually machined out with a smaller cutter, a 1/4 inch flat end mill that we're going to use, and that's what I had done in class. And then these holes are going to be drilled. Often when you see smaller holes like this in the design in the class, they're for fasteners like rivets and screws. You can always check within Inventor to see the size. So if we go inspect and measure, you can click here and see the diameter. The 0.196 diameter is a very popular size that we use within the shop because it is the size for a number 10 screw. It's a clearance hole. Looking at the tap and drill chart, we see that a number 10 screw, if we look at a close fit clearance hole for a number 10 screw, it uses a number 9 drill bit, which has a diameter of 0.196. So that 0.196 is a common hole size that we use. It's so common that we have a drill bit in the machine dedicated for that hole size. Whereas these two features will not be drilled, they will be machined with, like I said, a 1/4 inch end mill that will cut away the material. So going back to the CAM tab here, we have our work coordinate system set up for operation 1. And that's what the XYZ is and the origin there. We've set all of that up. And so now it's time to do the steps. So let's first do the drilling operation. I think that's the most straightforward one. We're going to drill these 4 holes. And so we're going to hit drill. The first thing that we want to do is choose a tool. Now, if you've downloaded the tool library that I've made available, you can go and hit here on the tool and scroll all the way down until you see the tool libraries. Let's do this on the VF3 machine. That's the one I demonstrated in class. And so if we open this up, we get a kind of a whole bunch of tools available to us. And it takes a minute to kind of dig through, but if you look at tool number 16 right here, it is a drill bit that is 0.196 inches in diameter. The 135 degrees basically tells you the angle of the point of the drill bit. But so we have a drill bit. You can kind of see here where it says type, it says drill. This is just information about where it was purchased and things like that. And then here we have a defined spindle speed already. Okay, so when I set up the tool library, I defined kind of the speeds of those tools. And I usually chose a speed that worked well for aluminum. So if we're drilling something else, we might want to choose a different speed. But for now, at this level of class, we're just going to click on tool 16 and hit select. Now, if you did not get the tool library, what you're going to want to do is go up to like inch tools. Maybe you can go inch aluminum and start looking for a drill that is the right size. And you'll eventually find one. 0.196 should be in there. Looks like they have 2 to choose from right here. Well, actually, one. I'm sorry. Right there, 0.196, a number 9 drill bit. The tip angle is a little bit different, but that's fine. And you would choose that drill bit. Okay. So for here, choosing tool 16 and going select. The next thing that I want to do is actually select the geometry of what I want to actually be cutting. Before I do that, I want you to kind of see these speeds. It says feeds and speeds, or feed and speed. This is for a later lesson, and we get more into this in the advanced class, talking about how fast the spindle should be running, how fast it should be diving into the material, and things like that. And so the plunge feed rate is how many inches per minute it's moving downward. And all of these things, again, are a little bit beyond our level, and basically at least this level for a first introduction. So we're going to go to geometry here, and we can actually select the geometry. And if I can click each one individually, and that's easy enough when there's 4. But notice you can say select holes of the same diameter, and it will just select all of those. And there are more features here, but for us, that's all we need to select those holes. And then the next thing is, how deep do we want to go? Well, there's a number of options. You really don't have to worry about, for right now, the clearance height and the retract height. That's how the machine moves when it comes up to move away and above the material. So you can kind of see it's going to drill a hole and then move up to, this height, which is the retract height before it goes to the next hole. And so you can, it's defined right now as the stock top plus 200 thousandths or 0.2 inches. And typically you can leave those settings as default. The times when you would change those is if maybe you have to ensure that maybe there's something on top of the part, like a clamp, and you drill a hole and you want to make sure that the drill bit comes up high enough to clear the clamp before it drills the next hole. You could then change the retract height and the feed height to increase that distance, as I changed it there. But for now, we're going to leave those settings as default. The one setting that we do want to change is the hole depth. Right now it says the bottom height is going to be at the hole bottom. But if we look at this, and I'm going to actually turn the piece here, you can see the shape here of the drill bit coming in. And so if the tip of the drill bit goes to the bottom of the hole, it leaves all of this material. And we don't want to leave any of that material. And so what you really want to do is click this button where it says drill tip through the bottom, and it ensures that the tip goes through and so that the sides of the drill bit make it to here. But then I typically add on an additional distance. Okay, so you can have what's called a breakthrough depth. And so I recommend, especially since this is a hollow tube and there's nothing below it, an air, we can add in a significant breakthrough depth. Typically, I'm like 20 thousandths of an inch. Sometimes you can go more. Notice if we do 20 thousandths, we're here. We could even go, 40 thousandths and nothing is going to happen. And so just make sure that you have a little breakthrough depth so you're not having to worry about cleaning that up afterwards after it's machined. So now we have the holes. The holes are drilled with tool 16. We have this here. If you wanted to change anything, you could just double click. You could change the tool, which we don't need to, but anytime you would want to change something, you can. The last little tab that I skipped was what type of cycle. And there's many different types of cycles. Since this is such a shallow hole, all we need to do is just punch the hole in and come out. But sometimes you need to do some peck drilling, like going in and pulling out where the drill bit pulls the chips out, and especially in deep holes, there's a lot of different options here. But for now, we're just keeping this as the default setting. Now that that's done, we want to start looking at the other two features. And as I mentioned before, we're going to be using a 1/4-inch flat end mill to machine out those two features. I'm a big fan of using the 1/4-inch flat end mill for most of the operations in the class like this for a couple of reasons. One, it's a large enough diameter that you can cut at a reasonable speed. You don't, if it's a tiny end mill like an 1/8 inch or smaller, you have to really go slow because you could break it pretty easily. But a 1/4 inch is a large enough diameter that has more rigidity and you can machine a little bit more quickly. Also, it's not so large that if we do end up breaking it, it's not horribly expensive to replace. A typical end mill of the quality we use in class is in the $20 to $25 range. But if we step up to like a 3/8 end mill, which again you could machine things much more quickly with that, um, because it has a larger diameter and it can cut more material and it has more rigidity as you move it through the material. It costs more if it breaks. And in an educational setting, we really have to worry about balancing learning with cost and things like that. And in an educational setting, there we are more prone to making mistakes just because we're having so many people learn the steps. And so having a 1/4-inch end mill is a really good default size for us. And so you'll see me using that a lot, even though we could use something larger. So one thing to realize is this corner needs to have a large enough radius so that the 1/4-inch end mill could actually machine it. And if we go inspect and measure that, that has a radius of 0.15 inches. Now, a 1/4-inch end mill has a diameter of 0.25, but that means it has a radius of 0.125. And that is less than 0.15. So yes, the 1/4-inch end mill can definitely hit that radius. Typically, when we're designing parts, we have the designers give something above 1/8 of an inch for the radiuses on their corners there. If it is tighter, then we have to move to a smaller cutter to make that corner. Okay, so going back to the CAM tab, now that we've measured it and ensured that the 1/4-inch end mill will indeed work, we're going to click CAM here. And under 2D milling, there is a drop down, but we're just going to use what's up here, the 2D adaptive clearing. And notice it gives a little description. It says 2D adaptive clearing creates a roughing operation that uses more optimized tool paths that avoids, abrupt direction changes. Okay, tapers and angles can be defined for any walls or islands. That the walls and islands again is a more advanced part, but for us, we're just kind of cutting away here, and we're using a 2D adaptive clearing. Notice there's a 3D adaptive, and that's for parts that have definitely more 3D or three-dimensional shapes to this. Yes, this is a 3D part, but the feature is just really just a straight down two-dimensional cut there. So we're going to do just 2D adaptive. The tool that we're going to choose is a 1/4-inch flat end mill from the Haas VF3 tool library. Since this, I do have a couple 1/4-inch end mills. Notice I have a number 4 is a 1/4-inch flat stub length end mill, and tool number 5 is a 1/4-inch just flat end mill. Basically, the stub length, if we look at the two difference in the model on the lower left, you can see that the flat end mill number 5 is longer, and the stub end mill is just shorter. It's stubby. And the reason for a stubby length is it's more rigid. It doesn't stick out as far, and you can actually machine a little more quickly with it. And so really what we do care about is how long the flutes of the end mill are. And in fact, that is defined somewhere over here. Maybe we have to double click on the part and look at the tool itself a little bit in more detail. Sorry. Oh, I messed up here. Basically, I was trying to show the actual length of the flutes of the tool. And so let me actually click down here and go edit. And we can actually look at it there. And you don't have to worry about this too much, but we want to make sure that the flutes are indeed long enough on the cutter, this part. And the flute length of this is 0.375 inches, which is 3/8 of an inch, which is plenty long because the thickness of our tube is only 1/8 of an inch. And so for most features, I recommend using the stub end mill if it's available in the library. So we'll choose this one. We'll go select. If you did choose tool number 5, it would work and it would still machine the part. And so now that we've chosen the tool, I'm going to go to the next tab, which is geometry. And I'm just going to select this arc here. Okay. And this here. And then I'm going to go to depth. Basically, the same concept. Here we have a flat end mill. The difference is the bottom height is currently defined as the selected contours. What we really want is to go below that. And so I could choose something else here, or I could just do an offset. So I selected the top. I want to go at least to the bottom plus a little bit of breakthrough. This is 1/8 of an inch thick, which would be 0.125, but I want to go a little bit more. So I might make it like another 15 or 20 thousandths. If it was 0.125, I could go to 0.14, maybe 0.145 or even 0.15. There's nothing below it. It's just air, but we're going to put a negative in. And so let's just go to negative 0.15. So that's an additional 25 thousandths of an inch. And we'll then go to the next step. The next steps, we're not going to really change much except the stock to leave. Okay, this is saying, hey, we're going to leave a little bit of material left because this is what we call a roughing operation. Doesn't leave a nice smooth edge. We're going to come back and clean it up later. So we're going to leave a little bit along the edges, which is the radial. And 20 thousandths of an inch is pretty nice. But the axial, which is really the depth, how deep we're going, we don't want to leave any. We don't. But that would change how deep the cutter is going. So we're just going to say no. There's 0 stock to leave in the axial. We'll leave 10 to 20 thousandths of an inch in the radial. Okay, it's defaulted at 20, so we'll just leave that there. Here are some more settings that we'll talk about later in a more advanced lesson. But that's basically talks about how the tool enters the material and how it leaves the material and things like that. And you'll kind of see there's a kind of a helical entry. That's what this is, the ramp type. And there's lead-ins and things like that we'll also look at. So I'm just going to hit OK. We'll kind of see how this looks. So you can kind of see the helical entry. The tool enters the part. Notice it doesn't dive into the part just in a straight line. That would really damage the cutter. And so it gently enters the material with this helical path, and then it goes down and cuts the material, comes back out, and does the next part. But it's going to leave 20 thousandths of an inch around the perimeter. You can kind of see that if I hit simulate. We can go over here and simulate what's going to happen. You can actually kind of show the stock material too. You can kind of see it's digging into the material, and then it's using this adaptive strategy to clear out the material. Okay. So now that we've done this, the next thing that we want to do is come back and clean up these edges. And there's a couple ways to do that. We're going to use what's called a contour. and we can click 2D contour and select the actual geometry and do that. There's another way, which is still using a contour, but instead of, let's say we had 20 different features we selected, and we didn't want to have to reselect all 20 features. For 2, it really doesn't matter. We have the rectangle and the circle. But let's say we wanted to save some clicks. We could actually right click and go down here where it says create a derived operation. And we can code 2D milling, and we can go to 2D contour. And what that does is it keeps the same tool that we used, and it keeps the same geometry, and it keeps the same depth. So it keeps all of those things for us. And in fact, that's what we want to keep. We're going to keep the same geometry, the same depth. We're using the same tool, except now we're just going to kind of follow the edge. A contour is just follow a line to make the cut. Now, the one thing that I do want to point out, and I don't think we're going to change anything, is you can like repeat the pass. So let's say you wanted to make it ensure that it's really smooth. You could actually go over it again. Okay, and so you could have multiple passes to make sure that you're cleaning up the material. And maybe there's a whole bunch of material in the width that you have to cut up or cut off in the radial direction. You could do that in steps. Again, that's for a different lesson, different week. But what we do want to do is I just want to point out also the lead in. Notice these features. You have what's a lead in radius, a sweep angle, and a linear lead in distance. And I'm just going to hit OK. We're not going to change any of those things. Typically, the default settings here are going to be fine, but I want to show you what that actually does. So I'm going to hit OK. You can kind of see that the part actually doesn't dive, or the tool doesn't dive right at the edge. It dives away from it. Then it leads in with this little arc, and then it goes all the way around, and then it leads out with this arc. And so if I go back here and change some of these settings, maybe I want to change the angle to 45 degrees, and hit OK. You can kind of see that it's now coming in at a 45-degree angle. Okay, so that's what those settings do. And I can also maybe change the linear lead in distance to 0.1 inch. Okay, and now it comes in, has this arc, and then, which is a lot longer than it was before. Okay, so that is what those settings are. And sometimes we need to play around with them to get them the way they were. So I'm just going to leave that at the default. I think this was 0.025. Notice this is just the lead in, but I have the lead out the same as the lead in. But if you didn't want it to be the same, you could actually define your lead out, how the tool leaves the material to be something different. So I can hit OK. Now we've gone and we've cleaned up the material that we left before. Okay, the final thing that I want to point out is the actual cutting off the end. Okay, so if you remember when we cut the stock goes a little bit longer than the actual part. And so what we want to do is cut the part to length. And we're going to do that with a contour. Okay, so I'm going to hit 2D contour. Notice I'm not creating a derived operation because I'm not using the same geometry and stuff. But I'm going to do a 2D contour. And then I'm going to select this edge. But before I click the edge, I'm going to hit Alt and then left click. And that just selects this edge. If I don't do that, notice if I go to contour and just click the edge, it goes all the way around. I don't want to do that. So I'm going to clear the selection, hit Alt, left click, and then that gives just this edge because I just want to come and cut this edge. The tool I'm going to use, notice it keeps the same tool that you used in the previous operation, which is what I want, the 1/4 inch end mill. The depth, same settings. I'm just going to go negative 0.15 or 150 thousandths down because I want to make sure that I go all the way through the 1/8 plus a little bit. The two things that I do want you to change is one, the cutting feed rate. When we're cutting this way, we're cutting the full thickness of the material. We're making a big slot, and that's a lot of force on the cutter. And for just a good rule of thumb, I'm just going to have you cut the feed rate, or you could just half the feed per tooth. Again, this, we haven't gone over the details of these numbers, but this is how fast the tool is moving through the material at 45 inches a minute. And that really is determined by the speed of the spindle, how much material you're cutting per tooth, and things like that. But if you just change the feed rate, it changes all the others for it. It changes the feed per tooth for you. So just as a good rule of thumb, anytime you're doing a slot cut with any of our cutters, just cut the speed in half. The final thing is under the lead ends. If you remember the curved lead ends, if I just hit OK and kind of see what's going to happen, if we do a top-down view, you can see that the tool dives in here and then spins around and then comes out. What's happening though is that the part is actually diving into material, or the tool's diving into material, because the material extends out. And so I don't want you to ever do that. And so what we're going to do is just under the linking here, the linking tab for that, is we're going to change the angle to 0, and we're just going to increase the linear lead-in distance to, we'll just go 0.15. Something, I'd prefer it to be larger than the radius of the part, or the tool. And the tool is 0.125. So I'll just go 0.15. We'll take a look at it. Again, the exact numbers aren't that critical as long as the cutter is safe. And so let's take a look at a simulation. So here is a side view. You can see the tool is going to come down, go through and cut, and then come back up. If I have this one highlighted and simulate, we can see that the cutter is not diving into the material. It's a safe distance away. And then it goes through and comes up. So now we're left there. And so that's the slot cut that I was talking about. So now what I can do is select the entire operation and go simulate. And we can see everything. The drilling, the helical entry onto the adaptive cutting, or the adaptive clearing. You can see that it's leaving a little bit of material along the walls that it will come back and clean up with the contour. So now we're coming in with a contour, cleaning it up, and then we go to the end and do the end cut. We'll talk in later videos how to actually create the code for the machine.